Now we'll see about lateral shift. So first of all, we'll see what is lateral shift. Suppose you can take a glass slab, which is a transparent slab of thickness T. A light is incident here. Suppose incident angle is I. Suppose if this slab is not placed, then what happen? This ray has to go like this. That dotted line, it shows the direction of the incident ray. And due to change in the medium, what happened? The ray will be refracted into the second medium. So for example, you can take this rarer media, air, and this is a glass, that is denser media. Refractive index is mu. So it bends towards to the normal. So now what you get, this angle, that is R. Actually, the angle between this dotted line, that is I. And refracted angle is R. That refracted beam is incident on the second surface of the slab. That is refracted into air again. It coming from rarer media to denser, again denser to rarer. So here air, glass slab, and again air it comes. Finally it comes into air. That means here again it will be refracted. You know these two angles are, this is R and this also are alternate angles. So two parallel lines, these two are alternate angles, those two are equal. And this refracted angle is equal to again I only. Why? Because you see it enters in air, from air to glass, here it leaves from glass to air. So finally both medium are same. That's why angle of incidence, final angle of refraction, both are same. Already we discussed about that concept. These two rays are parallel. That means this dotted line, that ray, initial incident ray and final refracted ray, both are parallel, but they have some parallel perpendicular distance between them. That only what we call lateral shift. There is no deviation in the angle, and finally the whatever the emergent ray, that comes parallel to the incident ray. So but a small shift sideways, it shifts. That what we call lateral shift. A perpendicular distance between these two is called lateral shift, that is represented with x. That is, you have to calculate DC. That only what we call lateral shift. To calculate that, first you can assume a bigger right angle triangle, that is OAC. Using triangle OAC, what you can write, tan I is equal to. So this angle, that is opposite by adjacent. Opposite is AC. By adjacent from here to here, OA. OA nothing but T only, thickness of the slab. Similarly, using smaller triangle, this one, this right angle triangle here, 90 degrees. So using triangle, that is OAB, tan R is equal to this small angle. Tan R is equal to opposite AB by OA. AB by OA nothing but T only. First you calculate BC, and after that we can calculate X. How to calculate BC? From this you can write what is BC? BC nothing but AC minus AB. So BC is equal to AC nothing but T tan theta. T tan theta nothing but tan I here they gave. Minus AB nothing but T tan R. T tan R. So BC is equal to T take common. What do you get? Tan I minus tan R. This is about from B to C. You see, in this triangle, this is the perpendicular foot. This is the perpendicular distance between the two parallel lines. So here 90 degrees, that is hypotenuse, and we need to calculate this side. That means if you know this is I, this must be 90 minus I. So again this is I. We need adjacent. We know hypotenuse. This is the hypotenuse, and X we need, that is adjacent. So to calculate that adjacent, that is CD. CD is equal to what you can write here. So BC cos I. See that adjacent now. So cos I is equal to X by BC. So you can write CD is equal to, or X equal to BC nothing but I'll write that value T into tan I minus tan R into cos I. So like this we can calculate lateral shift. If you know incident angle and refracted angle and thickness of the slab, we can calculate like this. Otherwise you can expand this, x equal to T tan I we can write as sin I by cos I minus sin R by cos R into cos I is there outside. Now make it LCM. That what you get, x equal to T sin I cos R minus cos I sin R by cos I into cos R into cos I also there. Cos I get cancelled and only cos R remains there. This you see sin A cos B minus cos A sin B formula. So you can write sin A minus B. So x equal to T sin I minus R by cos R. This equation we can modify like this also, T into 1 minus cos I by mu square minus sin square I into sin I we can write. This is under root. Suppose if I and R are very small, the angle of incidence and refracted both are small, then what you can write, x equal to, in place of I minus R we can take T into simply I minus R. And if R is small value, R small value means cos sin I is equal to I, but cos I is equal to 1 you get. Why? Because very small value means nearly equal to 0. Cos 0 you are getting 1. That's why denominator become 1. Here take I common, that is T into I common, that is 1 minus R by I. Suppose if you take sin R by sin I is the reciprocal of refractive index, so we can write like this, T I into 1 minus 1 by mu also you can write. Then we can write this for small angle of incident and refractions. Of course, incident is small means refraction also small we get. Now we'll see about apparent depth. First of all, what is apparent depth? We'll see one example. Suppose you can take a beaker. Initially there is no water inside the beaker. A coin is placed at the bottom. Suppose the height of the beaker you can take it as something T you can take. T is the height. Now what they are doing, they fill this beaker with water or liquid, with liquid they fill. Due to refraction what happened, and the person who is observing from here, he feels that the coin little rises up. It will be appeared here. That is because of refraction. So the new depth of the coin from the surface of the liquid, that what we call T apparent. That is called apparent depth. Actual depth is T, but now the coin is absorbed at a depth TA, that what we call apparent depth. The shift in the position, that is actual depth minus apparent depth, that what we call apparent shift. And to calculate apparent depth, you can consider there is this you can take air refractive index is 1, and this is a liquid or water you can take refractive index mu you can take. So the person who stands outside, he starts observing the coin, or you can take an object which is placed at a T depth from the surface of the liquid. This is the surface of the liquid. Above this medium, air medium or vacuum can consider refractive index is 1, and below that refractive index is mu. Here is the object, and because of refraction, what happens when it enters from denser to rarer, the refracted ray bends away from the normal, so it moves away from the normal. The person who observes here the coin or the point object, he feel that the point is here, object is here. That means if you extend this line and backward, this angle is r, so we get this angle also r. We get here is the image he is observing now. So this depth, what you call here to here, last time from surface of the liquid to object is actual depth t. Now from the surface of the liquid to image, this is apparent depth t apparent. You can write t apparent here as show like this from here to here. So take that this point as something AB already we use, and this you can use as center C. C2O is actual depth and C2I is apparent depth. So this angle is I, means this also I, and use tan theta formula using this triangle, that is OC, and name that this as something as D. Using triangle OCD, and what you can get, tan theta is equal to, or tan I is equal to opposite by adjacent. Opposite is CD, by adjacent is T. Actually it is OC, nothing but actual depth of the object from the liquid surface. And using this small triangle that is CID. So using triangle CID, tan R is equal to, for that also adjacent, opposite by adjacent. Opposite is CD, by adjacent is T apparent. Take ratio of these two, tan I by tan R. You can take tan I by tan R is equal to, what you can write, tan I. So CD by T by CD by T apparent. So reverse you get T apparent by T we get. If theta is very very small, that is I and R values are very very small, you can take tan theta is equal to sin theta. That means tan I is equal to sin I and tan R is equal to sin R. Then what you get? This is sin I and this is sin R, which is equal to T apparent by T. You know, this is a refractive index formula. Refractive index is equal to mu is equal to sin I by sin R. So here we can use, if this is a mu1 and this is mu2, we can write like this, that is mu1 by mu2 we can write. Why we are writing mu1 by mu2 means from where to where light enters. So here it enters from mu2 to mu1 medium, second medium to first medium. That's why you get refractive index reverse we are getting mu1 2. Otherwise we can write this equation. We can write mu2 to 1, which is equal to mu1 by mu2. So mu1 by mu2 is equal to sin I by sin R here. But here, you know, if angles are very very small, in place of tan I you can use sin I, in place of tan R you can use sin R. From that what you can write, this is equal to tan I by tan R, that is equal to T apparent by T we can write. Yeah, from this equation what you can say, T apparent is equal to, here T apparent is equal to, that you can write as T into mu1 by mu2. So for example here you can take what is mu1 is 1 and mu2 is mu, so that you can take T by mu you can write. So the apparent depth is T by mu. And what is shift in the position? Actual depth is T and a new position is T apparent. So that you can write T common 1 minus 1 by mu you can write. So apparent shift and apparent depth. You can write like this. You see, for example, here and object is on denser medium and observer is in rarer medium. So what happen if it is become reverse? If it is become reverse, in place of mu1 take mu and in place of mu to take 1. Suppose and light ray enter from air to water. Then in that case what you can get this T apparent, you get reverse ratio we are getting. So T apparent is equal to, here in that case T apparent, TA is equal to mu into T we get. Shift in the position, delta T is equal to mu minus 1 into T. Actually T minus TA, that is TA is mu into T, and we get like this. From this what you can conclude, you see that here it is less than actual depth. Apparent depth is less than actual depth. If the observer is in the rarer media and object is in denser media, so what he feel? He feel that the distance of object is less than actual depth. Suppose if the person is in denser media, object is in rarer media, so the person inside the water start observing outside things, outside object. Then he feel that it is far away than actual where it is. So that's why you get T apparent is mu into T we get, mu times increases. Here by mu we are getting. So this is about apparent depth and apparent shift. Now let's see about one of the application of apparent depth. You can take different mediums. Suppose you can take first media has refractive index mu1, second medium refractive index mu2, third medium has refractive index mu3. They place an object here, and thickness of third medium is T3, T2, T1. These are the thickness. What is the real depth? Suppose if observer is here, a person is here, what is the real depth? Means this total is a real depth we have to take. The real depth or T is equal to T1 plus T2 plus T3 we can take. That is the real depth. What is apparent depth means? We know according to apparent depth formula, what is apparent depth? T apparent is equal to T by mu. So when person observes from rarer media and these mediums are denser, then you can take like this. These are rarer medium and these are the denser mediums. These are denser mediums when compared to that. Then we can take like this. T apparent is equal to T by mu. So from that, and what you get, T apparent is equal to, for first part T1 by mu1 plus, for second part T2 by mu2 plus T3 by mu3 we can write. This is apparent depth, actual depth, and this is apparent depth. What is the shift? Shift or delta T you can take. Shift is delta T. So T1 into 1 minus 1 by mu1 plus T2 into 1 minus 1 by mu2 plus T3 into 1 minus 1 by mu3. Like this we can write. This is the total shift in the image. So real depth, apparent depth. So real depth minus apparent depth, we get like this. That's what we call apparent shift. Now let's see one of the application on apparent depth. Suppose you can take this is the interface of the two mediums, and a bird is flying at a height. Here is the bird, and which is at a height h, height from the surface of the water. There is a fish below the water surface. You can take a fish at a depth d from the surface of the water. The refractive index of this medium is mu1 and this refractive index of the second medium is mu2. So of course you can take air this one and air refractive index you can take it as 1. Afterwards we can substitute that value. First you take and one of the person or body is observing from a medium which is having refractive index mu1 and the fish is at depth d inside the liquid which is having refractive index mu2. So before observing this concept, we will see about one concept already we discussed that suppose you can take an object is here in a medium which is having refractive index mu2 and observer you can take person who is there in the medium 1 that is refractive index is mu1. If this depth is t, actual depth what we call what is apparent depth? Apparent depth formula we get mu1 by mu2 into t. T actual depth and mu1 from which media person observes and mu2 in which media object is placed. This is the formula we have. From this what you can how you can calculate and what is the distance of the fish when observed by the bird. So we can write like this: distance of the fish with respect to bird. That we can take like this. Suppose if d is the actual depth and for that what you can write d into mu1 by mu2 plus this height also you have to add. Why? Because when a person observes from the surface of the liquid it appears like this, but he start observing from here, that's why that height we can add directly h. Suppose same thing if you take and how fish start observing. Suppose if fish observes the bird, what is the distance of the bird with respect to fish? Distance of the bird with respect to fish is, and what is the distance of the bird in the other media? Here is observer, so it can take distance of the bird from the surface of the interface from h into and what you have to take mu2 by mu1. That is when fish observes from the surface of the liquid and above this height will be changed like this. But this distance also we can add. So how we are getting means observe is in which medium, that distance can take directly. Suppose here fish bird is observer, so height of the bird from the surface that we can take directly. Other one multiply with relative refractive index. Similarly, suppose if fish observing the bird, that distance we are taking directly d, and other distance that we multiply with relative refractive index. Suppose we can take this is in air, so refractive index is 1. Here it is in water, refractive index is mu. Then what you can take, what you get formula from this. So distance of the fish with respect to bird is mu1 is 1, mu2 is mu. So what you can write h plus d by mu you get means bird observes the fish near or less distance than actual. So bird feels that fish is actually here, but it feels somewhere here. Neither. And what about you get second case? Distance of the bird with respect to fish. If fish start observing the bird, then what you get? Actual distance d we can write plus d plus and mu2 is mu and mu1 is 1. So we can write mu h. Mu h means more than h we are getting. Here d by mu less than d. So actual depth is h plus d, but here you get less than h plus d we get. Here you get more than h plus d. So what fish observes the bird and it is more than actual distance. Now see if bird or fish is moving, what is the relative velocity? relative velocity of the fish with respect to board. So differentiate both sides with respect to time. Then what do you get? Velocity of the fish with respect to board is equal to differentiation of h is constant, that is constant differentiation is 0, and d differentiation, change in dy, change in time, is velocity of the fish. So we can write velocity of the fish by refractive index mu. You can write like this. Suppose here mu2 and there mu1 means what you can write here, you can write mu2 into mu1, that we can write as here mu1 is 1 and mu2 is mu, that's why you can write like this. And second case, and what is the velocity of the board with respect to fish? In that case, velocity of the board, differentiate here, d is constant and mu h is variable here, velocity of the board into mu. Mu nothing but you can take that mu2 by mu1, that is mu vp, like this we can write. So velocity of the fish with respect to board and velocity of the board with respect to fish. Now see one of the application on apprenticeship. Suppose you see these green color lines, these lines are converging beam of like is there, they are introducing a transparent glass slab which is having refractive index mu and thickness t. Because of it, what happened, first they diverge, the rays are diverges, and again at second surface they converge and they form image at different position. So actually without this slab it will be converge at O, now it converges at I. So the difference in the position, what we call shift in the position because of this glass slab. So that is the same formula what we get in case of apparent shifter. This is the formula, same formula we get for this also. So T is the thickness and mu is the refractive index. Then instead of focusing point at O, it will focus at point I. Similarly, if you take diverging rays which are going like this. So O is the source of rays, you can think, and they are diverging. So if you are not introducing any slab, they go like this, but instead of introducing this slab, what happened? First they converges, then again they diverges, and finally we get here the image. The distance between initial position, object and image, you can think this distance you can take it as x, the shift in the position of the, and converging, actually it is not converging, diverging point, the shift in the position of diverging point. Now see one of the application of apparent shift. With the help of this we can calculate refractive index of any liquid, we can calculate any medium. Suppose for example you can take a traveling microscope, we can take which is focused. Traveling microscope is focused at a fixed distance. Suppose initially you can take a beaker, and this traveling microscope is focused on the base of the beaker, that is you can take you can place a coin at the bottom, it will be focused there. They note that the distance of focusing as R1, reading 1. Now they fill this with some liquid, so they fill up to a height h, think. Now again they try to adjust this microscope until it focuses the surface of the liquid. Then they note as a reading as R2, reading in the second case on focusing on the surface of the liquid is R2. And after that they start focusing, keeping the height of the liquid like that only. They start focusing the new position of the coin. Actually coin position shifted a little bit because of refraction, it appears somewhere here. Now they start focusing the coin, and whatever the focusing reading, that they note it as R3. Now what is actual height of the liquid? That is h. H is equal to, we can write R2 minus R1. Why? Because R1 is focusing on bottom and R2 focusing on the surface of the liquid. The difference only height of the liquid we get. What is the shift in the position from here to here? Shift in the position here when it is focused, what is the reading? That is R1. When it is focused here, what is the reading? That is R3. R1 on the bottom, R2 on the surface of the liquid, R3 on the surface of the, means on the image, new image. So it appears like little rise. So what is the shift in the position? Delta H. Delta H is equal to what you can take R3 minus R1. We know relation is there between delta H and H. Of course, we are using T and delta T. So delta H is equal to H into 1 minus 1 by mu. So those readings you know, that is R3 minus R1 is equal to R2 minus R1 into 1 minus 1 by mu. With the help of this, we can calculate what is the refractive index if know those three readings. Okay. Otherwise, if you know H and delta H, from this you can calculate delta H by H is equal to 1 minus 1 by mu. Send this mu that side, 1 by mu is equal to here 1 minus delta H by H. Mu we can take, or 1 by mu is equal to, first we make LCM. H by H minus delta H. With the help of this formula we can calculate refractive index. If you know reading R1 is reading on the bottom when the telescope or traveling microscope is focused on the bottom, and R2 is on the liquid surface, R3 is on the image new position of the coin.